Picture this. The year is 1966. The Cold War is at its absolute bone-chilling peak. Two superpowers, the United States of America and the Soviet Union, are locked in the most consequential technological race in human civilization's history. Every rocket launch is simultaneously a scientific achievement and a geopolitical declaration. Every satellite in orbit is a message sent not to the stars, but to the enemy across the Iron Curtain. Both sides are pushing the absolute limits of human ingenuity, engineering, and willpower. Scientists are sleeping in their offices. Marriages are breaking apart under the strain of impossible deadlines. Entire cities of research are oriented toward a single purpose: beat the other side into space. And in this atmosphere of unimaginable pressure, something extraordinary happens. A small Soviet spacecraft, roughly the size of a beach ball, weighing under 100 kilograms, drops silently toward the moon. There is no atmosphere to slow it down, no parachutes, no runway, no safety net of any kind. Nothing between this fragile metal sphere and the cold, ancient, rock-hard lunar surface except a set of retro-rockets firing at precisely the right moment, at precisely the right angle, with precisely the right amount of thrust. One miscalculation, even a fraction of a second off, and the spacecraft becomes just another piece of shrapnel scattered across the lunar regolith. Another failure, another crater, another expensive obituary. But the rockets fire perfectly. The spacecraft touches down, gently, impossibly gently. For the first time in the 4.5 billion year history of the moon, something built by human hands is sitting on its surface. Alive, operational, transmitting, sending back the first close-up photographs of another world. That spacecraft was Luna 9. February 3rd, 1966. One of the greatest moments in the history of exploration. Not just space exploration, but all exploration. Columbus spotting land, Magellan completing his circumnavigation, Hillary standing on Everest. Luna 9 belongs in that exact conversation. Because what the Soviet engineers accomplished that day had, just a decade earlier, been considered categorically impossible. The moon was not a destination. It was a dream. And on that February morning, the dream became a photograph. But the story begins even earlier. Because the real turning point came in September 1959, when Soviet probe Luna 2 became the first human-made object to physically reach the surface of another world. Luna 2 didn't land softly. It deliberately impacted the moon at high speed. But that crash was intentional, and it was historic in a way that is hard to fully comprehend. For the first time, something built in a factory had crossed 384,000 kilometers of absolute vacuum and touched another celestial body. The moon was no longer just a light in the sky. It was a destination, a world you could touch, if only for the obliterating instant of impact. That single event transformed cosmic dreams into engineering reality. Once you've proved something is possible, demonstrated it empirically, undeniably, nothing is ever quite the same again. The conceptual barrier between imagining and doing collapses entirely, and the race is on. The modern puzzle: why are we still crashing? Fast forward nearly 60 years. It's August 2023. We live in an age of artificial intelligence, quantum computing, reusable rockets, and smartphones more powerful than the computers that guided the Apollo missions. And Russia, the country that pioneered lunar soft landings, the country that gave us Sputnik, Gagarin, Luna 9, launches a new mission to the moon, Luna 25, and it crashes, not dramatically, not in some Hollywood fireball visible from backyards. It just crashes, silently, unceremoniously. The spacecraft, attempting a braking maneuver before entering low lunar orbit, fires its engines for too long. The trajectory shifts. Luna 25 swings too close to the surface and impacts at speed. Mission over. Russia has added a new crater to the ancient lunar surface and a new entry to the ledger of expensive failures. Think about what that means. Russia, the nation that invented lunar soft landings, the nation that put the first satellite in orbit, the first human in space, the first probe on Venus, that Russia failed to land on the moon in 2023. This should disturb you, and it should make you ask a very obvious question. Why? Before you reach for the easy answers, budget cuts, brain drain, political instability, consider this. Luna 25 was not alone. In the same year, ISpace, a Japanese private space company, attempted to land its Hakuto R mission 1 spacecraft on the moon. Japan, a country whose technological reputation is legendary worldwide, and the Hakuto R spacecraft crashed into the lunar surface. Post-mission analysis determined that the spacecraft had incorrectly estimated its altitude, a navigation error that, in the lunar environment, is instantly and absolutely lethal. And go back to 2019. India, in one of its most ambitious missions ever undertaken, attempted to land the Chandrayaan-2 Vikram lander near the South Pole. Hundreds of millions of people followed the telemetry in real time. Prime Minister Modi was physically present at ISRO mission control. And then, with just 2.1 kilometers between the lander and the surface, communication was lost. The lander had deviated from its planned descent trajectory. It struck the moon at a fatal angle and speed. The images of scientists with their faces in their hands were broadcast around the world. Russia, Japan, India, 3 nations with sophisticated space programs, proven track records, experienced engineers, all failing to land on the moon within a few years of each other. What is going on? The answer is not incompetence. The answer is not bad luck. The answer lies in the fundamental, unforgiving, almost hostile physics of the moon itself. Physics that do not care about your budget, your national pride, or how many simulations you ran back on Earth. The moon's gravity is not what you think, a hidden menace. Let's start with something that sounds basic, almost textbook, but is actually deeply and dangerously weird. The moon's gravity. You already know the moon has gravity, roughly 1/6 of Earth's, 1.62 meters per second squared. You've seen the Apollo footage of astronauts bounding across the surface in slow-motion leaps. Gravity on the moon. Simple. Understood. Predictable. Right? Wrong. Completely, dangerously wrong. The moon's gravity is anything but uniform. Unlike Earth, where billions of years of geological activity have distributed mass with relative consistency, the moon is a geologically ancient, largely static world, with enormous variations in subsurface density. The result is that the moon's gravitational field is lumpy, uneven, full of invisible ridges and valleys of gravitational force that cannot be seen from a descending spacecraft, but absolutely can and do throw spacecraft off course without warning. Scientists call these irregularities mascons, mass concentrations. They are regions of the lunar subsurface where unusually dense material is packed together, creating local gravitational anomalies that pull on passing spacecraft in directions and with magnitudes that the navigation computer never anticipated. Mascons were first discovered in the 1960s, when engineers noticed that early lunar orbiters were mysteriously drifting from their precisely calculated paths. Something was pulling them, something invisible lurking just beneath the surface of this supposedly simple, dead world. The strongest mascons are concentrated above the ancient impact basins, the vast circular plains that dominate the lunar near side. These basins were created billions of years ago when enormous asteroids slammed into the young moon. The impacts excavated huge volumes of rock, but also allowed dense material from deep within the lunar interior to flow upward through fractured crust and solidify near the surface. That dense material is still there, billions of years later, quietly exerting its influence on anything passing overhead. And then there's the South Pole. And here the story gets genuinely strange. In 2019, researchers at Baylor University published a landmark study in Geophysical Research Letters. Using data from NASA's Grail mission, two spacecraft that spent months precisely mapping the moon's gravitational field by measuring infinitesimal changes in the distance between them as they flew in formation. The team detected something extraordinary buried beneath the South Pole Aitken Basin. An anomaly, a massive concentration of dense material beneath the surface. Their estimate of its mass, approximately 2.18 times 10 to the 18th kilograms, roughly 2 quadrillion tons. For context, take all the water in all of Earth's oceans, multiply that mass several times over, and you're approaching this number. An almost incomprehensibly vast concentration of density hiding beneath the moon's south polar surface. When this discovery was announced, the internet did what it always does. Speculation exploded. Alien spacecraft, buried megastructure, ancient lunar base. But the scientific evidence points to a more mundane, though still fascinating explanation. The South Pole Aitken Basin is one of the largest confirmed impact craters in the solar system, approximately 2,500 kilometers in diameter, wide enough to cover most of the continental United States, and nearly 8 kilometers deep in places. The researchers believe the dense metallic core of the impacting body did not fully vaporize. Instead, it sank deep into the lunar mantle and remained there, locked in place by the moon's geological stagnation. The result is a gravitational anomaly of breathtaking scale, one that creates navigation challenges for any spacecraft attempting to orbit or land in the South Polar region that simply did not exist for the Apollo missions, which deliberately targeted flat equatorial nearside plains. The signal delay, decisions made in dead time. The gravitational irregularities are just the beginning. Let's talk about something that sounds like a minor technical footnote, but is actually one of the most dangerous aspects of any lunar landing: communication delay. The moon is 384,400 kilometers from Earth. Radio signals travel at the speed of light, approximately 300,000 kilometers per second, and take roughly 1.25 seconds to cover that distance one way. Round trip, about 2.5 seconds. That doesn't sound like much. In everyday life, 2.5 seconds is trivial. You wouldn't notice it in a conversation. On a spacecraft descending at 50 to 100 meters per second, 2.5 seconds is an eternity. Here is the brutal mathematics. At a descent rate of 50 meters per second, the spacecraft travels 125 meters in those 2.5 seconds. That is the full height of a large office building, traversed vertically, before a ground controller on Earth can even receive the signal showing that something has gone wrong, let alone transmit a corrective command. By the time that command arrives, the situation has already evolved. The spacecraft has moved. It may have already impacted. Think about it viscerally. Imagine driving on a narrow mountain road at night in fog, but with a mandatory 2.5-second delay between when you turn the steering wheel and when the wheels respond. At highway speed, that delay is fatal. You'd go off the cliff before your correction could take effect. That is essentially the situation ground controllers face during lunar final descent. They are not driving. They are watching a delayed video of someone else driving, with absolutely no ability to intervene in real time. This is why lunar landers must be capable of fully autonomous, real-time decision-making throughout the entire final descent. They cannot wait for instructions from Earth. They must sense their environment, detect obstacles, assess their own performance, recalculate trajectories, fire individual thrusters with millisecond precision, and execute complete landing sequences entirely on their own, without any human input whatsoever. Programming this kind of autonomous intelligence is extraordinarily difficult. The landing environment is complex and variable in ways impossible to fully simulate in advance. The surface is uneven. The gravity is anomalous. The lighting in polar regions, where permanent shadows can conceal craters and boulder fields, is treacherous. And every single decision the autopilot makes must be correct, because on the moon there are no second chances. There is no abort and try again, no pull-up and go around. Once a lunar lander commits to powered descent, it is absolutely committed. It will either land or crash. Those are the only two outcomes physics allows. Mars is paradoxically easier, the atmosphere advantage. Here is something that genuinely surprises almost everyone. Landing on Mars, vastly farther away, substantially larger, far more hostile to human life, is in certain critical respects easier than landing on the moon. The reason is simple. Mars has an atmosphere. Yes, the Martian atmosphere is extraordinarily thin, about 1% of Earth's density at sea level, but it exists. And that thin, frigid whisper of carbon dioxide makes an enormous engineering difference. When a spacecraft enters the Martian atmosphere, it experiences aerodynamic drag. Friction between the heat shield and onrushing molecules decelerates the vehicle, converting kinetic energy into heat and light. Then parachutes deploy, huge supersonic parachutes that use even the thin Martian air to slow descent further. Finally, rockets fire for the terminal phase. This multi-stage braking gives Mars landers something precious: time. Time to sense the terrain, time to identify hazards, time for hazard avoidance algorithms to run without racing a fuel clock. The Mars Science Laboratory mission used a sky crane maneuver, a hovering rocket stage that gently lowered Curiosity on nylon cables before flying away. A sequence that would have been completely impossible on the moon, requiring seconds of stable hover time that only atmospheric deceleration made available. The moon has none of this. Its exosphere is so vanishingly thin that aerodynamic braking is, for all practical purposes, exactly zero. A spacecraft approaching the moon experiences no air resistance whatsoever, right down to the surface. This means the entire deceleration burden falls on rockets alone. A spacecraft in low lunar orbit moves at roughly 1,680 meters per second, 6,000 kilometers per hour. It must slow from 6,000 kilometers per hour to a gentle vertical descent of a few meters per second using only engine thrust, while simultaneously navigating, avoiding hazards, managing fuel, and maintaining attitude control. Every kilogram of propellant was manufactured on Earth, quality checked, loaded on a rocket, carried 384,000 kilometers, and must arrive at the right place at the right instant. Even SpaceX's revolutionary Falcon 9, with its spectacular vertical booster landings, relies critically on Earth's atmosphere. The grid fins that flip out from the returning booster are purely aerodynamic control surfaces. They generate lift and drag only in an atmosphere. On the moon, they would be as useful as wings on a submarine. Lunar landers must do everything with rockets alone. It is a colossally more difficult engineering problem than any terrestrial or Martian analog. Apollo 11, 15 minutes that almost ended everything. Let's talk about Apollo 11, July 20th, 1969. Neil Armstrong and Buzz Aldrin descending toward the Sea of Tranquility in the Eagle lunar module. The world below, 4 billion people on 7 continents, was watching on television or listening on radio. What most of those people didn't know was just how close that mission came to catastrophe in the final 15 minutes of descent. Several minutes into the powered descent, the onboard computer, a revolutionary but severely limited device with less processing power than a modern digital wristwatch, began flashing an alarm code. 1202, then 1201. Armstrong and Aldrin exchanged a glance. Neither had seen these codes in any training simulation. At Mission Control in Houston, the room went silent. Steve Bales, the 26-year-old guidance officer, had less than 10 seconds to decide: abort the landing or press on. The 1202 alarm indicated executive overflow. The computer was dropping lower priority tasks to keep critical guidance functions running. Bales made the call. Go. But there was a second problem, potentially more immediately dangerous. As Armstrong finally saw the surface clearly through the forward window, he realized with growing alarm that the guidance computer was flying them directly toward a large, rocky crater, perhaps 180 meters across, its floor littered with boulders the size of small buildings. West Crater. Landing there meant certain destruction, probable death. Armstrong overrode the computer. Without announcement, without asking Houston's permission, he took the hand controller and flew the Eagle manually, lower, slower, extending the trajectory beyond the crater field, searching for a clear landing patch. Mission control consoles showed fuel alerts. A voice called out, 60 seconds, then 30 seconds. Armstrong found his patch of ground. He set Eagle down with the precision of someone who had trained for this exact scenario his entire career. The contact probes on the landing legs touched the surface. The blue contact light illuminated. Armstrong cut the engine. Houston, Tranquility Base here. The Eagle has landed. Post-mission analysis determined that approximately 25 to 30 seconds of hover fuel remained. Had Armstrong needed one more minute to find a clear spot, the mission would have been aborted under conditions that were themselves dangerous. The scenarios were not survivable. The lesson is essential. Without Neil Armstrong, brilliant, supremely experienced, psychologically unshakable, able to look out a window and override an imperfect computer in real time, Apollo 11 might have ended in disaster. The computer alone could not have saved it. A ground controller in Houston, with a 2.5-second communication delay, could not have saved it. Only a human being, physically present in the spacecraft, capable of instantaneous intuitive response, navigated that crisis successfully. You cannot put Neil Armstrong inside every robotic lander. That is precisely the problem. That is the fundamental limitation haunting every autonomous lunar mission, from Luna 25 to Hakuto R to Chandrayaan 2. The spacecraft is capable, but it is not adaptable. It can only execute what its programming anticipated, and the Moon has a persistent, lethal talent for surprises. Why the South Pole, the ice that changes everything? So why are we trying to land at the South Pole? Why not return to the flat equatorial regions where Apollo landed so successfully? Why make this harder than it needs to be? Because the South Pole has water ice, and water ice changes everything. For decades, planetary scientists theorized that permanently shadowed regions near the lunar poles might harbor ancient deposits of water ice. These are craters positioned at such extreme angles to the sun that sunlight never penetrates their floors. Not seasonally, not occasionally, but never. For billions of years, these regions have been in total, permanent darkness. Temperatures plunge to approximately minus 250 degrees Celsius, colder than the surface of Pluto. Any water molecules arriving there, from cometary impacts, asteroid strikes, solar wind delivering hydrogen atoms, would freeze instantly and remain frozen for geological eternity. The evidence accumulated steadily. NASA's L-Cross mission in October 2009 deliberately crashed a spent Centaur rocket stage into the permanently shadowed Cabeus crater near the South Pole and analyzed the ejected plume. The result was unambiguous and historic. Water ice confirmed in significant quantities. Then in 2018, using data from the Moon Mineralogy Mapper instrument flown on India's Chandrayaan-1, NASA scientists published direct spectroscopic observations of water ice exposed at polar surfaces, not theorized, not inferred, directly observed. Water ice on the moon is not merely scientifically interesting. It is strategically, economically, existentially transformational for space exploration. Here is why. Water is H2O, hydrogen and oxygen. Split that molecule using electrolysis, requiring only electrical power, which solar panels can provide in the sunlit regions just outside the permanently shadowed craters, and you get molecular hydrogen and molecular oxygen. Cool those gases sufficiently, and you have liquid hydrogen and liquid oxygen, the most powerful chemical rocket propellants available. The very propellants that powered the space shuttle's main engines. The very propellants the Saturn V used to send Apollo missions on their trans-lunar journeys. This means lunar south polar water ice is a potential in-situ propellant source. Spacecraft could be refueled at the moon rather than having to carry all propellant from Earth. A fuel depot at the South Pole could serve as the first link in an interplanetary supply chain, ultimately reaching Mars, the asteroid belt, and beyond. The economics of deep space exploration change entirely when you don't need to lift every kilogram of propellant out of Earth's deep gravity well. This is why everyone is racing toward the South Pole. Russia, India, Japan, China, the United States, and a growing constellation of commercial companies. The water ice may be the key that unlocks the rest of the solar system. The orbital geometry of polar missions, a completely different kind of difficult. Apollo had it comparatively easy in orbital mechanics. Missions launched from near equatorial Earth, flew direct trajectories to the moon, and entered equatorial lunar orbit. Descending to the flat near-side equatorial planes was relatively straightforward, essentially a two-dimensional geometry problem. Getting to the South Pole requires a polar orbit. The spacecraft must orbit from pole to pole, crossing the equator at right angles. This demands entirely different orbital insertion maneuvers, different approach trajectories, and far more complex three-dimensional navigation. From a polar orbit, the spacecraft must time its deorbit burn to within fractions of a second to arrive above the South Pole at exactly the right orbital moment, with exactly the right velocity vector. Miss that window, and the opportunity is gone for that pass. Wait for the next orbit, burning precious fuel while the Aitken Basin gravitational anomaly quietly nudges the orbit further off course. Then there's the terrain itself. The South Polar region is nothing like the Sea of Tranquility. It is not a vast, flat lava plain. It is a landscape of extreme topographic relief. Crater rims rising kilometers above surrounding terrain, valleys plunging into permanent darkness, mountain massifs blocking communication and navigation signals, slopes at angles that would challenge any landing system. Landing here requires centimeter-accurate targeting and millisecond-precise execution that was simply unnecessary for equatorial Apollo sites. China demonstrated that non-equatorial polar missions are possible when Chang'e 4, in January 2019, became the first spacecraft in history to soft land on the far side of the moon, itself a mission so technically demanding that it required a dedicated relay satellite in a halo orbit around the Earth-Moon L2 Lagrange point, just to maintain communications with a spacecraft permanently shielded from Earth by the lunar body. That achievement proved the technical difficulties are surmountable. But the far side was still not the polar south. The South Pole remains the ultimate test. The failure archive, a history written in craters. Let's put the modern failures in honest historical context. The popular narrative, that we used to be able to land on the moon and have somehow forgotten, is misleading in ways that obscure the real lesson. The very first American lunar mission, Pioneer 0, was launched in August 1958. It exploded 77 seconds after launch. Pioneer 1, Pioneer 2, Pioneer 3, all failures. The early Soviet Luna missions, mostly failures in their initial phases. Between 1958 and the mid-1960s, The combined success rate of all attempted lunar missions by both superpowers was roughly 20 to 30%. 7 out of 10 missions failed. That wasn't a crisis. That was the expected cost of operating at the frontier of human capability. The American Ranger program, designed to return close-up photographs before crashing into the moon, was a masterclass in persistent, expensive, institutionally humiliating failure, followed by eventual success. Rangers 1 and 2 failed to reach proper orbit. Ranger 3 missed the moon entirely, sailing off into solar orbit. Ranger 4 reached the moon but transmitted nothing. Ranger 5 missed the moon. Ranger 6 hit the moon perfectly, but its camera system failed to activate. A heartbreaking near miss, delivering zero scientific return. 6 consecutive failures spanning 3 years and hundreds of millions of dollars. Then came Ranger 7. July 31st, 1964. It returned 4,308 close-up photographs of the lunar surface before striking the sea of clouds. Ranger 8 and 9 followed, both successful. The data from those 3 missions formed the critical foundation upon which Surveyor and Apollo were built. Surveyor fared better. 5 successful soft landings from 7 attempts. A success rate around 71%. Still far from perfect, but dramatically improved. And then Apollo, 6 successful crewed landings from 7 attempts, the 7th aborted due to Apollo 13's oxygen tank explosion, itself resolved into the most extraordinary rescue mission in spaceflight history. The historical pattern is unmistakable. The path to reliable lunar landing runs through failure, many failures. Expensive, visible, sometimes heartbreaking failures. Luna 25, Hakuto R, and Chandrayaan-2 Vikram are not signs of civilizational decline. They are signs that humanity is once again attempting something genuinely difficult in a new and more demanding operational theater, the lunar South Pole, and paying the historically inevitable tuition of early failure. Chandrayaan-3, failure transformed into mastery. Which brings us to Chandrayaan-3. And this story deserves to be told in full because it is one of the most satisfying narratives in recent space exploration history. After the heartbreak of Chandrayaan-2's Vikram lander in September 2019, the tears in mission control, the worldwide news cycle, the diplomatic condolences, the engineers and scientists of ISRO went back to work. They did something that is harder than it sounds. They looked at their failure honestly, not looking for excuses or someone to blame, but genuinely trying to understand, at the deepest technical level, exactly what had gone wrong and why. The Vikram lander had encountered a control system issue during final descent. The software was designed to handle velocity errors within certain parameters. When the actual velocity error appeared outside those parameters, the control system struggled to compensate, and the lander descended too fast at a fatal angle. A subtle, interacting series of factors had cascaded into catastrophe in the last 2 kilometers. ISRO's response was methodical and profound. They didn't just patch the specific failure mode, they rebuilt the entire approach to landing safety from first principles, adopting a failure-based design philosophy. Instead of optimizing for the best-case scenario, they systematically designed for every worst-case scenario they could imagine. What if a sensor fails? What if a thruster underperforms? What if the South Polar gravity anomaly shifts the trajectory unexpectedly? For every failure mode, they built in redundancy, margins, and fallback strategies. They expanded the acceptable landing zone, increased fuel capacity, added more powerful processors and higher resolution hazard detection cameras. August 23, 2023. Just days after Luna 25 had crashed. The world's attention was briefly on lunar landings, drawn by the spectacle of the Russian failure. Chandrayaan-3's Vikram lander executed its powered descent sequence. The guidance system performed within its expanded parameters. Hazard detection cameras identified a clear landing patch. thrusters fired their final braking pulses. Vikram touched down, softly, cleanly, permanently, in the lunar South Polar region. India became the fourth country in history to successfully soft land on the moon, and the first ever to achieve a soft landing near the South Pole. Mission control at ISRO erupted. Engineers who had experienced the gut-wrenching silence of 2019 were now on their feet, embracing, weeping openly. Prime Minister Modi, watching via video link from the BRICS summit in Johannesburg, told the nation, "India is now on the moon." The Pragyan rover deployed from Vikram's ramp and began rolling across the ancient South Polar surface. Over the following 2 weeks, it confirmed the presence of sulfur, aluminum, calcium, iron, chromium, titanium, manganese, silicon, and oxygen in the surface material. Direct chemical measurements that no spacecraft had ever made from that region of the moon. The lesson is timeless. Failure, rigorously and honestly analyzed, is not the end of a mission. It is the beginning of genuine mastery. The engineers who failed in 2019 were uniquely, irreplaceably qualified to succeed in 2023 because they carried in their institutional memory the precise, hard-won knowledge of exactly how the system breaks down under pressure. No textbook, no simulation, no theoretical analysis can provide that knowledge. Only failure can. Robots at the frontier, from opportunity to ingenuity. While the South Pole tests human ambition, robots have been quietly demonstrating what autonomous exploration is truly capable of and where its limits lie. Consider opportunity. The Mars Exploration Rover launched in July 2003, designed for a 90-day mission, operated for 14 years and 136 days until a planet-wide dust storm in 2018 coated its solar panels and ended the mission. 14 years on another planet. More than 45 kilometers driven. Over 217,000 images returned. Compelling evidence of ancient water activity, sedimentary rock layers, mineral deposits that form only in liquid water, erosional patterns speaking of a Mars that was once far wetter and more hospitable. Then Curiosity, still operating in Gale Crater as of 2026, has driven more than 30 kilometers and made the pivotal discovery that Mars once possessed the chemical conditions, the right elements, the right mineral environment, potentially necessary to support microbial life. Not that life existed, not yet proven, but that it could have. The implications of that single finding reorient everything we understand about life's distribution in the cosmos. And Perseverance, which landed in Jezero Crater in February 2021, is actively collecting documented rock samples sealed in titanium tubes, intended for future retrieval and return to Earth. It also carried MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, which in April 2021 produced oxygen from the Martian atmosphere for the first time in history. A small demonstration. A monumental proof of concept for future human life support on Mars. But nothing has captured the imagination quite like Ingenuity. A helicopter on Mars. A vehicle using spinning rotor blades to generate lift in an atmosphere 99% thinner than Earth's. To generate sufficient lift on Mars, rotor blades must spin at approximately 2,400 revolutions per minute. Far faster than any helicopter on Earth, and the entire vehicle must weigh almost nothing. Ingenuity weighed 1.8 kilograms. Its first flight, April 19, 2021, lasted 39 seconds and reached an altitude of about 3 meters. It hovered, it turned, it landed safely, and humanity achieved powered atmospheric flight on another planet for the first time. By the time a rotor blade was damaged during its 70-second flight in January 2024, ending its operational life, Ingenuity had flown more than 17 kilometers and demonstrated beyond doubt that aerial reconnaissance is not just possible, but enormously practical on other worlds. What do these explorers teach us about the lunar South Pole? That robots, properly designed and given sufficient engineering margins, can accomplish extraordinary things in hostile remote environments. And that they break. They encounter failure modes no simulation predicted. They face terrain no designer fully anticipated. The answer is neither robots alone nor humans alone. It is both, each compensating for the limitations of the other. The next chapter, Artemis and the permanent lunar presence. The most ambitious lunar program since Apollo is underway. NASA's Artemis program, named for Apollo's twin sister in Greek mythology, aims not just to return humans to the moon, but to establish a permanent human presence there for the first time in history. Artemis 1, launched in November 2022, was an uncrewed test flight of the Space Launch System, the most powerful rocket ever flown at that date, and the Orion crew capsule, which flew a 25-day trajectory around the moon and returned safely, splashing down in the Pacific just 80 meters from its predicted landing point. A complete success. Artemis 2 will carry 4 astronauts, including the first woman and first person of color to leave low Earth orbit, around the moon on a free return trajectory. The first humans at lunar distance since Apollo 17 in December 1972. A shakedown cruise. Test life support systems, verify crew procedures, confirm Orion is safe for human occupation at lunar distances. No landing, but immensely consequential. Artemis 3 aims to land humans on the lunar South Polar region. The landing vehicle is SpaceX's Starship Human Landing System, a lunar variant of the largest, most powerful rocket vehicle ever constructed, designed to be fully and rapidly reusable, capable of landing substantial cargo and crew on the lunar surface and returning them to orbit. Alongside Artemis, the Commercial Lunar Payload Services Program, CLPS, is sending a series of small commercial landers to the moon. In February 2024, Intuitive Machines' Odysseus lander touched down near Malapert A crater in the South Polar region, the first American soft landing on the moon since Apollo 17 in 1972. Odysseus tipped slightly on landing, one leg catching on the surface, leaving it at an angle that reduced solar panel exposure. The mission was shorter than planned, but it was a soft landing, achieved, real. The commercial sector is learning quickly. The second generation of CLPS landers will incorporate lessons from Odysseus. The third will incorporate lessons from the second. Institutional knowledge is accumulating exactly as it accumulated during Ranger, Surveyor, and Apollo, but faster because more teams are working in parallel. More missions are flying more frequently, and far more sophisticated engineering tools are available for post-mission analysis. Looking up, the only perspective that matters. On a clear night, away from city light pollution, you can see the moon with your naked eyes in extraordinary detail. The dark Maria, ancient volcanic plains. The bright highland regions, scarred by billions of years of impact bombardment. The largest craters as bright spots near the limb, and somewhere near the southern edge of that pale disk, barely visible but unmistakably present, is the region toward which so much of the world's engineering talent and human ambition is currently directed. There is something profoundly humbling about this. That place you can see right now, that ancient, scarred, luminous face that has looked down on every human being who has ever lived, is an active frontier, not metaphorically, literally. There are spacecraft in orbit around the moon right now. There are instruments on its surface transmitting data. There are engineering teams in Houston, Bangalore, Beijing, Tokyo, and a dozen other cities planning the next missions, analyzing the latest data, designing the next generation of landers with every lesson of every previous success and failure embedded into every component. China's Chang'e 6 mission, in June 2024, successfully returned the first samples ever collected from the lunar far side. Ancient volcanic material, from the South Pole Aitken Basin, brought to Earth laboratories for the first time in history. The scientific implications of those samples are still being worked out. They may tell us things about the early solar system that no other collection of material can reveal. The Moon is not a relic of the 1960s space race, frozen in Apollo nostalgia. It is a living frontier, actively being explored with increasing ambition, increasing frequency, and 6 decades of accumulated hard experience. Every failed lander carefully analyzed, every successful touchdown that expanded our knowledge base, every gravitational anomaly mapped, every shadow probed, every sample collected, all of it building towards something unprecedented in human history. A permanent human presence beyond Earth. A species no longer entirely dependent on the continued stability of a single, fragile, irreplaceable world. We are not there yet. We may not reach that milestone for decades. The lunar South Pole will continue to test every mission directed toward it. It will break more landers. It will defeat more ambitions. It will add more entries to the ledger of expensive, painful, instructive failures. But it will not stop us. Nothing in human history, not distance, not danger, not cost, not repeated failure, has ever permanently stopped the exploratory impulse. The crashed landers are not gravestones. They are stepping stones, each one raising the floor a little higher, bringing the next success a little closer to inevitable. The next mission to the South Pole is already being prepared. Its engineers have read the post-mission reports from every previous failure. They have incorporated those lessons into their designs, tested and retested and tested again. And the mission after that will incorporate lessons from that one. Mission after mission, generation after generation, in the oldest and most reliable process available to our species, learning by doing. Keep watching the night sky. Keep asking the hard questions. Keep demanding that your species reach higher, push further, and never stop exploring. Because that light above you is not just a light, it is a destination. And we are going back. I hope you enjoyed the video. If you did, please hit that like button. It genuinely helps this channel reach more curious minds who care about where humanity is headed. And if you haven't subscribed yet, now is a great time, because we cover the biggest stories in space exploration every single week. Drop your thoughts in the comments below. Do you believe we'll see a permanent lunar base in your lifetime? Are robotic systems finally ready for the brutal demands of the South Pole, or do we still need human pilots in the loop? I read every single comment, and I answer as many as I can. Your engagement keeps this channel alive and growing, and it genuinely means more than you know. Thanks for watching all the way to the end. That kind of commitment from a viewer is everything to a creator. Stay curious, stay ambitious, and the next time you look up at the moon, remember, that is not just a light in the sky. That is a destination, and we are going back.